Hello everyone, we are FTC 23511, the Seattle Solvers, and today we're going to be talking about how to tackle complex designs through planning, specifically our multi-chassis and our Swerve. I'm Ajay and I'm our finance lead.
I'm
I'm
Ishan and
Socket. I'm Socket, and I'm our design lead.
I'm Ishan. I'm our outreach lead.
And I'm our software lead.
Okay, so a little bit about who we are. We are a fifth year first team, and this is our third year in FTC. Last year we had a top 6% OPR in Into the Deep, and this year, as of now, we have a top 4% OPR. We are an open alliance team, meaning all our CAD and code is public to anyone who wants to see it. And we compete in Washington, meaning our first competition is in early November, which gives us only about 2 months after kickoff to really get our robot into function. And competitions after that are about every 2 weeks. So last season, we decided to have a full robot rebuild between our interleague competition and our state championships. And we wanted to add a level 3 hang, but that was too overambitious and failed. As you can see, our OPR dropped from at interleagues from 134.48 to 120, showing that complexity in our design actually made our robot perform worse in the long run.
So going into this season, we made a lot of changes right from the off season. So in our planning, we are using the off season to essentially try out as many new mechanisms and learn as much as possible, which we mainly did through just building as many robots as we could over the off season. So on the right, you can see that's a turret mechanism we actually built over the off season for a wiffle ball shooter that Ishan will talk a little bit about later, and also a completely new robot for the Into the Deep season, which used carbon fiber, a power takeoff mechanism, and basically a lot of things that we wanted to try out, but we couldn't. And this planning change really helped us because we're able to try out these mechanisms in a low risk setting, and then we're able to better implement them in season as we did with Swerve, which we'll talk about. Um, Other thing with hardware is we really tried to make our mechanisms as modular as possible so that we could be able to iterate on them without doing a complete rebuild. So Ajay mentioned we did a full rebuild from interleagues to states last year, which was almost like less than a month. And we found that redoing everything from scratch actually took a lot of time and it wasn't as efficient because we were only making minor upgrades. So this year we tried to make our mechanisms mounted in a way such that from the very beginning, we're able to quickly take them off, improve them, and then reattach them on to save as much time during season. And then Ars can talk about a little bit about the software changes we also made.
So on the software, one of the biggest things that we did is we integrated full Swerve support and control into our open source library solvers live. This includes the kinematics, the controller that actually handles the movement, and a simple visualizer for easily creating paths, more of which we will be talking about.
So, one of the major projects we took on this off-season was making a multi-chassis. With focus on modularity in mind, this chassis has about 75 different mounting holes throughout. You can see like some of them, especially on this back plate here. It has four different configurations for our hub mounts from some just on this side, like from all of them on one side to what you see here with one on either side. Um, there's three different places for mounting odometry. Though we use like two wheel with pinpoint, it allows us to have some extra like uh, it has it allows us to like essentially mount the wheels in a way that this robot can work for any design. The point of this multi-chassis is essentially to function for any different archetype of robot. It can function as a swerve drivetrain or a mechanism, and it's kind of similar to the strafer chassis in that way where you can put essentially anything on it, you can turn it into absolutely anything, and this robot can work for basically any season. So the reason we did this in the off season was essentially to limit the amount of time we need to work on our robot during the season. We don't have to design a drivetrain if we have one that works for essentially every season, like built in the off season. So that was one thing we made. So I'm actually going to go give a bit of a CAD walkthrough on this one here. So first, let's start with the actual. drivetrain here. So you can kind of see this is the multi-chassis here I was talking about. This one has like Swerve modules in it. You can see on the bottom, like I was talking about earlier, you have those three odometry mounting points. These cutouts for Swerve module, which you can use either mechanism wheels or Swerve on. Um, yeah, so there's all these different mounting holes throughout the robot. You can see so many of them here. You have all these extra like random holes for bearings, all these screw holes, right? You can see these are actually motor mounting points here, right? So we have like over 75 of those throughout this robot here, just to allow us to mount basically anything anywhere, which as Socket was saying last year we had to rebuild our entire robot just to make minor changes to it. To add like a L3, we had to build the entire robot again from scratch. With this robot, all these mounting holes, we don't have to go do that because we can essentially make any change to this robot. We can move things around. We don't like need to worry about recutting new plates or anything like that. So it's kind of like a strafer chassis, except you're getting all the benefits of a parallel plate drivetrain and the custom like weight savings and everything in this drivetrain here. So best of both worlds. So we're going to go into a bit on how we like planned out something like this. So this is a master sketch here. For those of you who don't know what a master sketch is, it's essentially a series of sketches here that allow us to essentially plan out our robot without building it, like physically, or without having to go through and design the full thing. Do this before, like making the robot. It allows you to plan out where you're going to put every single item here. So you'll see, like, we have a bunch for our drivetrain here. You'll see, like, you'll see lots of different pulleys throughout, right? So, like, you can essentially mount anything here, right? These are all like major points we could find for different archetypes. So on the side you'll see we have like turret, shooters, like slide archetypes. So like last year the main one was two slide archetype and into the deep. Right? That was what we used in our robot. And like you can see here, we kind of planned for that even with our like robot this year. We want to make it able to function for that. So we added like all these different like bearing holes for pulleys and things if we ever have to make a robot like that, right? So um, you can see here, I'm going to go open up the plate so you can see kind of how it affected it. Uh, uh, so you can see here, these are the vertical slide mounting holes right here. This entire top lip of this plate is just to like account for the vertical slides here. And same thing for these holes on the bottom, right? Or these this like line of vertical holes. That's all just for vertical or for horizontal slides right here. You can essentially mount a 14-inch BWT link slide. Those are what we use on our robot, but you can use them like you can essentially make a two slide archetype on here, or you can do something like a like turret and a, a turret and like shooter kind of one. So this off season we actually tried to develop um a wiffle ball shooter robot. So you can see here, like active intake and everything all mounted on the same chassis, right? So general idea where you can mount essentially anything on here, right? So the idea of one of the other things we focused on, like I said earlier, was mechanism versus swerve. So in the planning, we actually have to involve like a lot of different options for it. If you want a chassis that can be used anywhere, you're going to need it to basically have a lot of different contingencies or possibilities for design. So one thing you'll see is we have three separate mounting options for Mechadem in case like depending on what the robot needs to do or what else we want to put on the robot that might take up the same space. You have these essentially like center mounted motors here. Then you have all these like you can have them mounted even like higher here where you have two stages of pulleys, right? Or you can even like go through a singular stage of gears. You have all these different options made because you want this chassis to be essentially as modular as possible. So like we can essentially build anything on this spot. So that was kind of the main focus here, modularity, which this robot is kind of like you can or this drivetrain is essentially something you can turn into absolutely anything, any type of archetype, any type of robot. So now Socket's going to tell you a bit about more about like the Swerve. Yes.
Yeah, I'm gonna share my screen to take over. Just
Okay.
a little bit before the Swerve, Arsh is going to talk a little bit about the software planning that also went into our change. So, yeah, Arsh.
Yeah. So one of the biggest things that our team did in order to make our Swerve successful on the software was working on our code without a robot. There's actually a surprisingly large amount of things that you can do without a robot to help you make sure that you can complete your tasks effectively. And this is really important, especially for us, because Washington is a very tight deadline. So especially after the first competition, you're going to have competitions coming out nonstop every 2 to 3 weeks. So one large factor contributing to our success in early league meets is that we actually theory coded a lot of our systems early while our robot was still being built. One thing that we did was our launcher math. So this is getting the velocity from the distance of the robot and other similar things for our turret and our intake. This is also including structure for our files, as you can see in the bottom right corner, which is effectively creating folders and directories and entry to help organize our code. This can all be done with our robot. Additionally, uh, teams can also learn about libraries. This is things like popular pathing libraries like Pedro Pathing or Roadrunner, or command-based libraries like our very own Solver's Lib or op alternatives like Next FTC and Mercurial. And then teams can also integrate them with each other and also create autonomous paths with visualizers uh, before just to make sure their team has enough time to actually test out everything.
Yep. So moving on to specifically Swerve, like how we were able to implement a complex mechanism. So there's going to be an overview of what we did with Swerve. So firstly, if you don't know what Swerve is essentially four different high traction wheels that are able to rotate in any direction, and essentially they give you increased traction and movement speed in all directions compared to Mechnum, which can be efficient while strafing or moving diagonally. And we really wanted to try it out because it would be potentially useful across seasons. It wouldn't be just used in one season, but theoretically you could use it every year, just like how teams use Mechanum every year. But however, it does come with a lot of difficulties because you are running four extra servos and sensors for figuring out where the wheels are actually facing. And all of these need to be operating efficiently all the time in both hardware and software. So in hardware, this means your power transmissions need to be efficient, so you're not pulling too much power. And also in software, you need to make sure you have good loop times, which Arsh will talk a little bit about how we optimize so that we have precise control over where the wheels are facing. So all of this, all in all, adds a lot of complexity for just having the basic functionality for your drivetrain moving. So it took us a lot of time to actually make this possible. So we actually spent our 2024 off season developing our Swerve drive, but we saw that it had issues with power draw, with accuracy, with also in software as well, that we weren't happy enough to use it in season. So we revisited it this off season. And then finally, we came up with the modules that we're currently using. And even then, they're still not perfected, and we still have things to improve on. So having these fallbacks, like in the multi-chassis, like Ishan said, are really important because if for other reasons Swerve doesn't work out, we always have the option to return to Mechnum and at least have a functional robot, so we don't end up having a worse competition season because of Swerve. So, like Ishan did with the multi-chassis, I'm going to talk a little bit about our 2025 Swerve module. I'm not going to go too much into our 2024 module, even though it is public. But the 2025 module, you can see it's a slightly bigger, but you can see it has a lot less screws and nuts, which is something we really tried to focus on in trying to make our entire Swerve a lot more modular and accessible. So starting out with how we make this modular, we actually split up our entire Swerve module into three different parts. So we start with the lowest level, which is the wheel. This is just a simple aluminum wheel with some tread on it, but you can see that it's modular within the next level, which is the pod. So by removing this screw and this screw, if we hide these two screws, in real life, you'd unscrew them. This entire axle over here and the wheel that's on it are basically able to slide out from the bottom. So we actually have a slot over here that allows you to just take this entire thing out the bottom. And we realized that using accessibility through the bottom of the robot was going to be very efficient because a lot of the times you have stuff on top of your server modules or on top of your mechanism wheels on your drivetrain. So, but there's not usually much happening below your robot. So we kind of made everything accessible from the bottom. Um, this also means that not only do we have the wheels modular like that, these four screws, if you unscrew these four screws, then we're essentially able to take out everything on this bottom half. So everything over here is just able to slide out and we're able to access anything. So if we need to replace the tread, like tighten any screws, anything like that, we're able to have access to that. But it doesn't just stop there because we go further in the next step of the module. We're actually able to take out the entire pod, so that entire previous subassembly. If you loosen some set screws at the top and you remove these four screws, again, accessible through the bottom, just so that we have like full control over being able to remove things. So if we hide these four screws, there's actually nothing constraining the pod from just being slid out the bottom. And again, we're able to access anything. So if we want to grease the gears because we want higher efficiency, if we need to re-grease them, then we can through that. Or if you need to tighten any screws, again, inside here, it just makes it a lot easier to do all that. And then finally, at the highest level, this entire Swerve module is designed as a module and not directly integrated into like a drivetrain, which has like one big plate, which has all four wheels and everything mounted onto it. Because we wanted it to be able to be replaced with these side mounting screw holes with these square beams. So this allows us to essentially unscrew the Swerve modules entirely. So if we want to like completely replace the module and replace it with mechanism, or if it's just sometimes easier to access, for example, the servo over here, if you take out the entire module, we also have the ability to do that. So this just gave us a lot of control over the previous year, which had a lot of like different screws that made it hard to access. It was also more compact, so it was harder to reach in there and do this. So these were all improvements that we've made. But this isn't ending here. We, because of this kind of modularity, we're actually able to improve our Swerve even during mid-season. So currently we have, we're planning to replace the treads that we currently have with a new molded tread. So you can see we're going to replace the wheel with a custom molded urethane tread. And this is possible because during the season, it's only going to take us maybe an hour to replace all four wheels because we can just unscrew these two screws, replace the wheel, and then pop it back in rather than having to design the entire Swerve in a way such that you have to take everything out to access it. So this is something we're still doing in progress, and it's just one of the examples on how modularity can help you. Now Arsh will talk a little bit about the programming side of how we made Swerve efficient as well.
Yeah. So the first thing that our team did when working on the Swerve on the programming side was create the kinematics for it. So we started off by simply using Desmos to derive the kinematics with first order. However, we found out that these theoretical kinematics, when implemented in code, simply weren't enough. We had to optimize it. This is a really big issue because with Swerve, you have a whole motor a uh and a servo for each module. So you have a lot more hardware to deal with. So one of the some of the things that we use for optimizing our code is that we use something called slew rate limiting to handle gamepad inputs and make driving smoother, as well as determining when we should actually be turning the pod itself with the servo or actually setting a motor power. Then to actually control the swerve, we implemented a P2P, also known as a PID to point, which moves in simple straight lines. We didn't want to opt for more complex curved paths because they were going to take a longer time to develop, and this was something simpler that could easily be done in the off season, which would give us plenty of time to prepare for decode season. So the way this works is this uses a PID controller for the heading, another PID controller for the translational movement in order to accurately move the swerve drivetrain from one point to another point. And we found that this was all we really needed in order to get a consistent yet simple autonomous. Then for the visualizer, we simply modified the Pedro pathing visualizer instead of building our own one, which is also open source. And we simply added the functionality to only create lines and to adjust paths as needed. And then, like I said, because Swerve has both a motor and a servo, that has a lot more hardware reads and writes than you expect. So this is going to cause an issue with loop times because the longer your loop times are, that means effectively you're going to have more latency with your robot because you aren't getting the most up-to-date values from where your hardware actually is. So the first thing that we do is that we do some pretty simple things like bulk reads and motor caching, which effectively groups in all of your hardware reads together instead of calling them individually. And then motor caching and servo caching to some extent prevents unnecessary calls. Additionally, one more thing about necessary calls. One of the biggest things that our team strives to do on the logic side is making sure we don't have any unnecessary set power calls or any other logic things that we don't need to. We're only setting the power only when we absolutely must. This helps reduce unnecessary things even on a logic side, not just a hardware side, but this is a failsafe as well. The final thing we do for our loop times is implementing a library called Photon. This effectively is a little bit more complex, but it removes the global write lock. And what that on the global thread write lock. And what this allows us to do is this allows us to write faster to hardware, even if this comes at the issue of having a slightly less stable SDK. But this took a lot of time to perfect and making sure that it was stable. So this is definitely something if teams want to look forward to, that they should definitely spend a lot of time looking for a lot of investing into this, not something they should take with a very little time. And finally, we have Solver's Lib. Solver's Lib is our open source FTC lib fork that integrates all of these features together with the standard FTC lib features. This includes Swerve, this includes the loop time optimizations, and everything above that I just talked about. And this is critical for making our Swerve work. Thank you
Yep.
for listening.
And thank you for listening. And if you have any questions, we can answer them here, or also you can go to the link tree and we have our contact information and our Discord server there.